Greetings. In this video, I will demonstrate how to do the Mercury eccentricity lab. Or this is the lab in which you will measure, using data from hundreds of years ago, you'll measure the eccentricity of Mercury's orbit around the sun. Remember, all of the planets orbit the sun in elliptical orbits, but Mercury's orbit is particularly eccentric. So let's take a look at this planetary configuration simulator, which we've already used. This showed up in the discussion of the Copernican measurements lab. So you already know what elongation is, but here's planet Earth, that's the outer blue planet. Here's Mercury, which is on an inferior orbit. And at any point in time, you can look at the angle between a line that goes to the sun and a line that goes to Mercury. So let me hit start on the animation here, and then I'll pause. So if you were on planet Earth, pointing the finger of your right hand towards the planet, and then a finger of your left hand towards the sun, the angle between those two directions we call the elongation. Right now the elongation appears to be 17 degrees, but as you watch the planet orbit the sun, it's going to go to the left of the sun, then to the right. You can see that down here. This is showing you what the view might look like from Earth. So it's oscillating back and forth on either side of the sun, but it never gets too far from the sun. It's always within, what, 20, 25 degrees of the sun. And that's because the orbit of this planet is an inferior orbit. And just like we saw in the previous lab, I'm going to pause when the elongation takes its greatest value. I think I did that right. This is the largest value that angle will take. It doesn't get any more wide open than that. Now, that's because this is a circular orbit. For an elliptical orbit, some of the elongations are slightly greater than others, but the average value would be around 23 or 22 degrees here. Yeah, 23, 22.9. Excuse me, 22.9 is closer to 23. Okay, and you'll notice, just like I pointed out in the explanation for the Copernican measurements lab, when the planet is at its greatest elongation, the line that goes from the Earth to the planet is tangent to the planet's orbit. And that's really the key to this entire lab. The observation that at greatest elongation, the line of sight from Earth to the planet, in the inferior planet, is tangent to the orbit. See that, how it only touches the orbit at one place? Now, let's look down here at the visualization of the way things would look from Earth. And I'll pause it right about now. Now, normally on a map, if up is north, then to the right is east and to the left is west. And that's what confuses people about this lab. Do you see how down here they're telling you that to the west, excuse me, to the right is actually west and to the left is east? That seems backwards from what you would normally do on a map. Again, if up is north on a map, then pointing to the right would actually be east. So what's up with this reversal of the cardinal directions? Let's go into Stellarium to answer that question. Here we are in Stellarium, and I'm going to highlight Venus here. Let me zoom out so we can see the ground. Do you notice which direction we're facing? South. The data that we're using today was collected by somebody in Europe in the 1500s. And Europe is in the northern hemisphere. And when you live in the northern hemisphere and you want to look at the planets, you have to face south. So most of the relevant scenarios would involve somebody facing south. When you are facing south, looking off to the right does correspond to looking west, and looking to the left corresponds to looking east. So if you're going to do this lab, I would make a note right now on the side of your paper that western elongation, west means right, and eastern elongation means left, because when we zoom in here on Venus and the sun, right now Venus is to the left of the sun. That's off in the eastern direction. So we would say that the elongation, excuse me, if I look down here, they're telling me it's 3 degrees. You would say that the elongation is actually 3 degrees east of the sun. And whoops, sometime later, let me fix the coordinate system here. And now Venus is over here. It's got a western elongation because it's on the right side of the sun. So west is right, east is left. Please write that down. It'll really help you as you proceed with this lab. And you don't want to take this value from stellarium in your lab. That's not going to get you a good grade. But let's take a look at Mercury, so we have some idea of what its greatest elongation is. So currently, Mercury looks to be quite a ways from the sun. If I look down here, well, sure enough, it's 23 degrees. That's about the value we saw for greatest elongation in the simulation. So if I speed up time and watch Mercury, I'm looking at the elongation. It's already decreasing now from 23 degrees. So it's going back towards the sun. See that? Now it's going to the other side. And the elongation, let's watch. Let me slow down just a bit. Let's watch the greatest value it takes now. 20, 19. Okay, so this time it only went out to about 20 and then decreased. So if you're wondering why the elongation, the greatest elongation changes, it's because Mercury's orbit is not really circular, it's eccentric. All right, here's Earth orbiting the sun. And remember, even Earth's orbit is slightly eccentric. The eccentricity is around 2%. And this is the picture that you should have in your head as you conceptualize how this lab works. And again, if you're on Earth looking towards Mercury, when Mercury is to the right of the sun, if you're facing south, that corresponds to a western elongation. Okay, so you'd have to look to the right of the sun to see the sun here, excuse me, to see Mercury that's off to the west. When Mercury is to the left of the sun, for somebody facing south, you would be looking to the east. And this graphic captures just the essence of the lab. In the lab is a table of data from, like I said, the 1500s. And somebody must have gone out every night and observed Mercury's elongation over a period of many years, at least a decade. And every time Mercury reached its greatest elongation, they noted the date. Because remember, Mercury is, since it's so close to the sun, it goes around the sun in just a few months. So you could actually repeat this a number of times over a period of just a few years. So this outer circle is the Earth's orbit, and they're showing you the dates on which the observations were made. So it looks like the Earth was going on counterclockwise in the order of increasing dates. And suppose June 5th was one of the dates on which Mercury reached its greatest elongation. I will demonstrate this on paper, but on that date, the greatest elongation would have been recorded. And the first thing you would do is draw a line from where Earth was. This is Earth's orbit. From where Earth was to the direction of the sun. And suppose the elongation was 20 degrees. The greatest elongation was 20 degrees on that date. Then using a protractor, you could draw a ray. See this purple ray? Off in a direction 20 degrees from the direction to the sun. Now remember, from the previous graphic, we know that a ray drawn from the Earth's position to the planet's position on a date of greatest elongation, that ray has to be tangent to the orbit of Mercury. Now, one line by itself, one tangent line, is not sufficient to tell you what the orbit looks like. But if you draw such tangent lines over a period of many months or even a couple years, then your tangent lines start to give you a sense of the shape of the orbit. Remember, each of these lines has to touch the orbit only once. So you can already see that the orbit has to lie within all these tangent lines. You can kind of see the ellipse. And notice that the sun is not at the center of the ellipse. The center is somewhere over here. The sun appears to be at one of the foci, or one focus of the ellipse. That's it. That's the entire lab. You will be drawing the tangent lines based on actual data recorded by somebody in the 16th century. And then once you've drawn the tangent lines, it's up to you to sketch in the ellipse and make a measurement of the ellipse's eccentricity. So you do have to be careful with your drawing. If you're sloppy, your results will come out terrible. So it takes a little bit of skill. So here's, somebody has attempted to sketch the ellipse that's tangent to all of these lines. Okay, and remember, the list of elongations that you will be consulting, those are greatest elongations. When you go back to the simulation, the ray that goes from the Earth to the planet, it's only tangent if we're talking about a greatest elongation, when it opens up to its largest value and then closes back up. Okay, so we need to review the vocabulary for an ellipse here. Remember, an ellipse has two foci, and these foci are equidistant from the center. Right? The distance here from the center to one focus is the same as the distance from the center to the other focus. And most people call that distance C. C is the distance from center to either focus. And then we use the letter A for half of the long diameter, also known as the major axis. So half of the major axis would be the semi-major axis. We use the letter A for that. And here's the definition of eccentricity. All you have to do is divide C by A. That makes sense because remember, for a circle, the two foci come really close together. Or maybe I didn't talk about that. For a circle, these two foci are practically on top of each other. So maybe you'd have a focus here and here. And then your distance C would be really small compared to A. A small number divided by a bigger number would give you a low eccentricity. That makes sense because we know that an ellipse that looks almost like a circle does have a low eccentricity. So the whole task here is to draw the ellipse and then measure C, measure A, divide in a calculator to get Mercury's eccentricity. And then you'll compare that with the value given in the lab handout, the accepted value. Now, I could multiply on top and bottom by the number 2, right? 2 over 2 is 1. So if I multiply on top and bottom by the same number, I'm not really changing the number. So you can also calculate the eccentricity by 2c over 2a. Well, what is 2c? C is the distance from the center to one focus. So 2 times c would be the distance from one focus to the other. I'm tracing that out. See that? This is 2 times c. And since you're measuring a longer distance, it's less subject to measurement error. So it would actually be better to measure the distance from focus to focus. And then you will measure the distance across the whole thing. Because 2 times a down here, 2a is the full major axis. So your task will be to measure the focus to focus distance, that's 2c, and then measure the major axis and divide the two. I think it's time to demonstrate that. Here's the paper on which you'll be drawing your plot. This outer circle represents Earth's orbit during the course of a year. And if I zoom out here, it's not real obvious, but I believe that this dot here, which represents the sun, is not actually at the center. And that's because this is not really a circle. This outer, quote unquote circle is really the ellipse of Earth's orbit, which is slightly eccentric. So the sun here would be at one focus of Earth's orbit. So what you'll be doing is looking at the list of elongations given. Let me scroll down to that page. There's a table here. They give you a whole bunch of greatest elongations. They tell you whether they're east or west. And the dates on which those elongations were measured are also given. So April 18th, for instance, that's when an eastern elongation was recorded by somebody in the year 1588. So April 18th. I go back to the plot here. April 18th. Well, here's the month of April. And they've only given us a few dates, 1st, 10th, and 20th. I want April 18th, so I have to figure out where the 18th is. Well, wouldn't the 15th be right in the middle of 10 and 20? Yeah, so from the 10th to the 20th, that's 10 days. 15 would be right in the middle. Well, 18 is 3 days after the 15th. So you have to interpolate. You have to figure out where April 18th is and put a dot there. And then the rest I'll demonstrate on paper here. I know the resolution is poor here. I'm sorry about that. It would be better if I could do this in OneNote with a Surface tablet, but I don't have one of those. So at some point, I may be bringing this close to the camera, like right now. Let's do the very first one, April 18th. we're told that the greatest elongation is 20 degrees to the east. So I'm going to, right now, I'm going to say that east corresponds to the left, and western elongations are when the planet is off to the right, just so I don't forget. Really, it's so you don't forget. Okay, April 18th, like I said. The 15th is right in the middle between 10 and 20. So I put a little mark halfway between 10 and 20. And now I'm going to go 3/5 of the way. 18 is 3 days after 15. So 3/5 of the way. That should be pretty good. So here's my dot. This represents where the Earth was in its orbit on April 18th of 1588. And I know that the planet Mercury was 20 degrees to the east of the sun as seen from the Earth. So the first thing you'll do is draw a line from the Earth's position on that date to the sun. And please do this lightly. You definitely want to use pencil. Your lab, it's not going to work if you use pen. It just will not work. Don't even try, because you have to erase a bunch of stuff. So lightly draw a line from the Earth's position to the sun, because you're going to erase that line. The only reason to draw that line, and I know you can barely see it, is so that you know how to position the protractor. So hopefully you picked up one of these. You can also print one out, but it's harder to use if it's a piece of paper because you can't see through it. So I need to draw a ray now that's 20 degrees to the east, which is off to the left, right? East is to the left. Okay, so I need to draw another ray that goes off to the left. So what I'll do, on my protractor, there's a little crosshairs. You don't use the bottom. You use this point right here, where there's like it says 0 degrees, or actually 180. This line here goes through that dot. So you have to put the dot on the Earth's position on that date. And then this black line on my protractor, if you're using a printed paper protractor, you might have to use the bottom edge. You need to look at the outside to figure that out. But for me, it's this black line. I need to line that up with the previous line that I already drew going from the Earth to the sun. See that? How this black line on the protractor lines up with the very light line that I already sketched. And hopefully you all have used a protractor or remember, but I need to draw a ray at 20 degrees. So see how the numbers up here say 130, 140, 150. That's if I was measuring angles from the other side. Obviously, I'm going to use these numbers. 10 degrees, 20 degrees, there it is. So this is the 20-degree notch. I'll put a little dot there. And if it wasn't 20 degrees, if it was like 23 degrees, you'd have to use the little notches here to figure out which notch corresponds to 23 degrees. But right now it's easy, it's 20 degrees. So I put a dot on the edge of the protractor out at that angle. And now I can draw the ray that goes from the Earth's position on that day through Mercury's position on that day. And this line, you can draw darker. Now, make sure you've done it correctly, because a lot of people, I'd say at least 1 in 4 people struggle with this lab, and the first time they do it, they've drawn their lines on the wrong side. Those are the 2 most common mistakes. Either you mixed up east and west, or you're not using the protractor right. And so your ellipse comes out really janky at the end. But I'm going to draw this fairly bold because I'm confident that I'm doing it correctly. And you don't need to go all the way to the other side. Go about 2/3 of the way. That should be good. 2/3 of the way should be good. Now remember, because the elongation that was listed here is a greatest elongation, I can be confident that this line is tangent to Mercury's orbit. So now that I've finished here, I can erase the Earth-Sun line because it just clutters up the drawing. What's up next? August 17th, the elongation was 27. Wow, those are really different numbers. Sorry, August 17th, 27 degrees. So let's find August 17th on here. Okay. Again, here's August 10th. The 17th, well, that would be 2 days after the midpoint. So midpoint, 2 days after, something like this. That's right about where planet Earth was on that date. And I will draw a very light line through the Earth and Sun so that I know where to put my protractor. I'm still talking about an eastern elongation, 27 degrees east. East is off to the left. So I put my protractor like this. Put the dot over the Earth, or the little circle over the Earth, and I make sure that this black line on the protractor lines up with the Earth-Sun line that I already drew. Wait a minute, what am I doing? I had it all positioned and then I lifted it off the paper. Okay, 27 degrees. Well, they give us 20, they give us 30. So this notch in the middle must be 25. 2 after that would be 27. So I put a little dot there, and now I can complete the ray. This is the ray through the Earth and Mercury on that date. I also know that this line is tangent to the orbit of Mercury. So you would continue that way all the way around. And you know what? I want to pick one that is, I want to pick a date like November 5th. Yeah, because I realized something last semester for the first time. On November 5th, the elongation was 23 degrees. Let's find November 5th. Okay. I know it's fuzzy, but this is November 1st. This is November 10th. This is November 20th. Now, I never really put much thought into this, and I always figured there's 10 days between November 1st and November 10th, but that's not really true, is it? What's 10 minus 1? 9. But 20 minus 10 is 10. So there's actually, to go from November 1st to November 10th is only 9 days, right? November 1st, and then you go 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th. That's 9 days. So the 5th, while November 15th really would be halfway between the 10th and the 20th, November 5th is not actually halfway from November 1st to November 10th. The 5th would be 4 days after November 1st. So we really have to go 4/9 of the way. Now, if you goof that up, it doesn't make a huge difference, but your ellipse will come out a little bit better if you observe that. So when you're doing a date that's between the 1st and the 10th of the month, you do want to try to take that into consideration. November 5th is 4 days after November 1st. So it should be 4/9 of the way from here, the 1st, to the 10th. So instead of going to the midway point, I'll just back up a little bit, and that should be sufficient. I'm not going to stress too much about it. So I would draw the Earth-Sun line. Yeah, and at least you can see that one now. And that's also an eastern elongation of 23 degrees. So I'll just demonstrate one more eastern elongation. .23 degrees, so I go out to the 20 notch and then 1, 2, 3 more notches on the edge of the protractor. I draw my tangent line, fairly bold, and I really do need to go back and erase the Earth-Sun lines. If you don't erase the Earth-Sun lines, it's going to be impossible to visualize the ellipse. All you want is the tangent lines remaining. Okay, let's do a western elongation now. Remember, if the planet is off to the west, then that means it's to the right of the sun, as seen by somebody living in Europe and looking at the planets. Okay, so the first one would be February 6th. And this is an example of what I was just talking about. There are only 9 days from the 1st to the 10th. February 6th is 5 days after February 1st. So we have to go 5/9 of the way. That's a little more than a half. So I'm going to put February 6th right about here. This is the Earth's position on that date. I will draw the Earth-Sun line lightly. And now, because the planet is off to the right of the sun, I have to position my protractor differently. Previously, I was doing this and drawing an angle that way. Now I have to flip this around. I'm still putting the circle over the dot that represents the Earth. I'm lining up this black line on the protractor with the Earth-Sun line. And since the elongation is, what did I say it was? 26 degrees. I'll put the dot right there. I can't even tell which dot I made because there's other marks on the paper.
There we go. See that? 0, 10 degrees, 20. Now I am using the outer numbers. Okay. I'll draw my line about 2/3 of the way across. I'll make it bold, and then I'll go back and erase the Earth-Sun line. I've only done 1, 2, 3, 4 lines here, 4 tangent lines. You have to do them all. But once you get the hang of it, it goes pretty quick. So that's the most labor-intensive part. And now I'm going to pause and pick up an old example so I don't actually do the whole thing here on video. Here you can see an example of a plot where all the tangent lines have been completed. The ellipse has not yet been drawn, but this diagram came out so well that you can very clearly see the shape of the ellipse. Remember, every one of these lines has to be tangent to the ellipse. There are no lines crisscrossing the middle or the interior of the ellipse because whoever drew this was careful to erase each of their Earth-Sun lines. You have to erase those lines, otherwise they're crisscrossing and you won't be able to see the ellipse. And at that point, you will have forgotten which lines were Earth-Sun lines and which ones were tangents. So make sure you erase as you go. This one came out really nice. Don't expect yours to be quite this good. Also, every semester, I don't understand this, but every semester, a significant number of people just kind of make it up. They just draw lines randomly. And frankly, the ellipse looks, it looks like a piece of crap. So don't there's no point to that. Obviously, I'm going to be able to tell the difference between just making something up and having drawn the tangent lines. So if it looks bad, you know you did something wrong. Like if you can't tell roughly what the shape of the ellipse is, if it looks all squashed, it means one or more of your lines was erroneous. And so you'll have to go back and check them, make sure you did east properly or west properly. I would try to check as you go, because it's really annoying to have to go back and, I've made a mistake, maybe the first time I did this. It's annoying to have to go back and figure out which of your lines was wrong. So please be careful with the protractor. It'll save you some time. Okay, at this point, you just do your best to sketch it in. And some of you will be better at this than me for sure. I'm just making light strokes with the pencil. I'm trying to make this curve so that it only touches each line once. See how this curve that I'm drawing only touches this tangent line once? It doesn't cross over any of the lines. That's the definition of a tangent line. Okay, so that's starting to look all right. And then what you can do is go back and trace over it more darkly if you want, now that you've sketched it. But I think this is sufficient. Notice how the sun is not at the center of this ellipse. The center would be something like that. This is off to one side. Okay, the next part might be the trickiest. It's up to you to figure out where the major axis is, because remember, we have to figure out the distance between the foci. We need to draw that other focus. Here's one focus. The other focus is probably over here somewhere. And both foci lie along the major axis. I can already tell that this is not the major axis because this is shorter than this distance. So you have to find the longest possible distance you can draw from one side of the ellipse to the other, such that the distance passes through this focus and through what looks like the center. Does that make sense? Like, it's pretty clear this is not the direction of the major axis because the distance from here to here is less than the distance from here to here. So you just have to eyeball it. You can take your ruler and kind of move it around. And to me, it looks like maybe this direction is the major axis. So I'm going to lightly sketch that, see if that looks about right. Yeah, it's pretty good. It's definitely not this direction. So once you've drawn the major axis, and if you turn this into me and somehow you got the eccentricity, but I don't even see a major axis, well, then I'll know that you just looked it up, because you can't do this without drawing the major axis. Okay, now we need to draw the other focus. Here's what you can do. Please use centimeters. See how my ruler's got inches on this side, centimeters on this side? Let's stick to centimeters. And even better than that would be to use millimeters. So from 8 to 9, for instance, is 1 centimeter, but that's been chopped up into 10 little pieces called millimeters. 3 centimeters is the same as 30 millimeters. 4 centimeters is 40 millimeters. So what I'm going to do first is measure from here in to the focus, because I know that the distance from this end to this focus is the same as the distance from this end to the other focus. I need to identify where the other focus is. So if I use my ruler here, it looks like, to me, it looks like this focus is 2.9 centimeters from here. See how I've lined up the 0 notch with the end of the major axis here? And when I do that, this dot is about at 2.9, or I could call that 29. See how there's 10 millimeters in each centimeter? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I could call this 29 centimeters. Now let me measure in 29 centimeters from the opposite end. So I'll put the 29, I'm sorry, not 29 centimeters, 29 millimeters. 2.9 centimeters, for instance, is the same as 29 millimeters. You just move the decimal place 1 to the right. Okay, so I'm going to put the 29 millimeter mark at the other end of the ellipse. That looks about right. And then I'll mark a dot at the 0 notch. And to be honest, this looks a little funky. These two look scooted over. I must have measured something wrong there. 29, okay. Oh, right, I had my ruler in the wrong place. So you do have to check your work. That's really where the other focus is. Yeah, I goofed that up. So let me erase this dot. Okay, so I've now identified the location of both foci. One of the foci is given to you, it's the sun. So remember, the distance from the center, this would be the center of the ellipse. The distance from center to one focus is what we call C, as in cat. But I'm going to calculate the eccentricity by doing 2 times that distance over 2 times the semi-major axis. In other words, the focus to focus distance, that's this distance, and the total major axis length from here to here. All right? Now, I'm not going to write down the numbers because I'm afraid that people will just copy my numbers, but let me just show you how to measure the focus to focus distance. If I put the 0 mark on the first focus, all I have to do is read off where this other dot is. And remember, this 1, that's 1 centimeter, that would be 10 millimeters. And, you know, just as an example, this middle line here would be 1.5 centimeters or 15 millimeters. But you want to be as precise as possible in measuring the distance from one focus to the next. That is the numerator here. That's 2c. Now, for measuring the major axis, you just go from here to here. Now, this is not 7 centimeters. You can see it's a little more than 7. But if it was 7 centimeters, you would multiply by 10 and call that 70 millimeters. 70 millimeters or thereabouts is what would go down here. Okay? So you can see that if you don't draw this carefully, if your ellipse comes out really janky, then your measurement of the major axis length will also be messed up, and you're going to get a horrible value for the eccentricity. So it does pay to be careful when you draw this. And the better you drew your tangent lines, of course, the better your ellipse will come out. And the more I look at this, I'm not even sure I've got the major axis in the right place. It's tough. It's tough to tell. Some people get really lucky and get a value for the eccentricity that's close to the accepted value. Now, here's an example of calculating E and doing the percent difference with the accepted value. So calculating the eccentricity. I'll use a pen here. So let's just suppose, I'm going to pick wrong numbers here so you don't copy them. Let's suppose that the focus to focus distance that you found was 21 millimeters, and that the major axis distance was 76 millimeters. Well, then you just put those numbers into the calculator. And by the way, in the handout, there's a page where some questions are asked. They ask for the distance between the foci in millimeters, not centimeters, in millimeters. Please put these numbers here. I'll be looking to see that you answer these questions. There's not much to fill out here. It's just those questions really, and then the last questions on the last page. Okay, so 21 divided by 76 is 0.276. 3 digits should be fine. Now, obviously, you shouldn't be getting that number because I made these numbers up. But they're telling us that the accepted value of Mercury's eccentricity right here is 0.205. That's the accepted value. And you're supposed to compute the percent difference between your value, or my value here, and the accepted value. So let me show you how to do that. You will be doing this in the space right here under the question, but I'm going to do it larger here. You take the difference between your value and the accepted value. This is my value, this is the accepted value, and we don't care about minus signs, so maybe your value is smaller than this, in which case the difference would come out negative. So just take the absolute value, and then you want to compare that to what it's supposed to be. Like, how much are you off by, and then how bad is that? Well, you have to divide it by what it should be, 0.205. And then lastly, of course, multiply by 100 to convert this decimal fraction into a percentage. So order of operations is important. Remember, your calculator will do division before subtraction. So I need to do this, 0.276 minus 0.205. Hit equals first. That's one way to do it. Okay, so this says that my answer is 0.07 higher or different from the accepted value. Well, is that bad? Is that good? 0.07, let's compare that now to 0.205. This is what it's supposed to be. So 0.07 divided by 0.205, that's a ratio of 0.34. Lastly, multiply by 100. So that would just move the decimal place 2 to the right, which is 34.6%. And we don't really need this many digits. How about you just round that? I'll call that 35%. So my measurement of Mercury's eccentricity is higher than what it should be by about 35%. That's not very good. Remember, I made up these numbers. You should be able to get a better agreement than that. Some people are lucky and they get really close, like 5% or less. Just do your best. When I'm grading this, if you're way off, if you get a number like 100%, that's not good. Some people think you're going for 100%. That's the goal. That's definitely not the goal. You want a low percent error. Now, don't BS it. It's fine to have a percent error. I would be surprised if you had 1% error. It's going to be more than that. I just want to see that you did the calculation correctly and that you followed the appropriate method for drawing the ellipse, okay? Just do the lab correctly. You don't have to get spectacular results. Okay, and then they've got a question about which orbit is more eccentric, more circular. Remember, hopefully you learned this in class, but the eccentricity of a closed orbit is between 0 and 1. The most eccentric orbit has an eccentricity close to 1. A circle is a special ellipse that has an eccentricity of 0. So the lower the eccentricity, the more circular the orbit. And then for this last problem, you can read the problem. I'm just going to direct you to the simulation. They're asking you whether this method would work for a planet outside the Earth. Right? Mercury is an inferior orbit. What if you'd like to determine the eccentricity of a planet that orbits well outside the Earth, like Pluto, for instance? So let me pull up the simulation again. So I will change the preset values here. I'll leave the observer on Earth and I'll put the target planet outside, like Mars. Now remember, how does this method work? There has to be a series of greatest elongations because that is when the ray that goes from the Earth to the planet, that's when that ray is tangent to the planet's orbit. Now right now, Earth is the inner orbit and Mars, for instance, is the outer orbit. So look at this ray that goes from the Earth to Mars and ask yourself if that ray is ever tangent to the orbit of Mars. The inside orbit is the Earth's orbit. Is that ray ever tangent to Mars' orbit? I'm just going to pause it a few times here. See the ray from Earth to Mars? It cuts through the outer orbit. Right there, it cuts through. In fact, it never actually is tangent to the outer orbit. There's also no greatest elongation. So whoever thought of this method in the 16th century recognized that when the planet reaches its greatest elongation, that's when the line is tangent. The ability to draw tangent lines to the orbit is what allows you to visualize the orbit. If you can't draw tangent lines, this method doesn't work. I think I kind of just gave you the answer. So you just have to find a way to put that in your own words convincingly, okay? Just make sure you put that in your own words. And that's it. So most of the time here will be, let's go back to the camera here. Most of your time will be spent drawing these tangent lines. If you goof up, just print out another one of these. Hopefully you have one of these protractors that just cost a couple bucks. Otherwise, you can print out protractors online. Good luck. And don't forget, when you finish, isn't it kind of cool that you can use measurements from hundreds of years ago to calculate the shape of Mercury's orbit? And conceivably, you could do this in real life. If you look at the dates here, 1588 all the way up to 1590. So just a couple years of observations would allow you to draw, well, you couldn't do this in real life in Long Beach because it's difficult to see Mercury. But you can come out to the desert where I am, and you'd have no problem doing this.